Hello, I'm Taekyung Kim, and I'm gonna present our work, Track, Perturb, and Explore, learning a feature alignment network for semi-supervised domain adaptation. This is a joint work with Chang Kim. Despite the promising success of deep neural networks in computer vision, these networks often show performance degradation when tested beyond training environment. Simple solution to address the degeneracy is to collect sufficient labeled samples on unseen environment. But the raw data collection and annotation requires huge amount of time and monetary cost. One alternative way to mitigate such demands is unsupervised domain adaptation. And another one is semi-supervised learning. Semi-supervised domain adaptation is an important task that bridges these two promising alternatives. Its goal is to synergize the few labeled target samples and the rich labeled source samples to generalize the model. Some may directly apply promising works of the unsupervised domain adaptation and semi-supervised learning, only with an additional supervision on the extra labeled samples, expecting that these promising methods will successfully work. However, a recent study reveals that such methods often show less effective or even worse performance than just training on the labeled source and target samples in the semi-supervised domain adaptation problem. To better understand the observation, we introduce a new perspective called intra-domain discrepancy, which is chronic in the semi-supervised domain adaptation problem. There are some factors in domain adaptation that determines the difficulty of the given adaptation scenario. For example, covariate shift, label shift, unique domain correlation, and the sparsity of the samples within the domain. Here, unique domain correlation means a common property that all samples in the domain share. Return to the subject in more details to these factors. The degree of the covariate shift or label shift affects on how many target samples are alignable and how much alignable such target samples are. How strong the unique domain correlation is affects on how much the alignable target samples can attract their neighborhood together into the decision boundary. And it also affects on how much the target domain can resist from the attraction. For example, like attraction induced by the related information between the source and target domains. Thus, in the unsupervised domain adaptation problem, if we are lucky so that if we have little covariate shift or label shift, then perhaps the source and target domains can be totally or partially aligned. But in general, the feature distribution of the target domain often tends to preserve the unique correlation of the domain, except some easily alignable target samples, as shown in the TSNE visualization. In contrast, since at least a few target labels are given in the semi-supervised domain adaptation setting, supervision on the labeled target samples enforces the corresponding features and their neighborhood to be aligned to the source feature clusters, regardless of how much the labeled target samples are correlated to the source domain. Thus, in some lucky cases, if the degree of domain shift is little or the target domain correlation is strong, then two domains may be successfully aligned. But in general, the target domain target feature distribution is deterministically separated into the aligned subdistribution and the unaligned subdistribution, causing the intra-domain discrepancy within the target domain. Here, we use the term subdistribution for representing probability distributions with total probability less than 1. And I'll call this by subdist for convenience. Such separation of the target feature distribution can critically affect on the conventional unsupervised domain adaptation approaches and semi-supervised learning approaches. Let's first begin with the semi-supervised learning approaches. Since the semi-supervised learning problem assumes to sample labeled and unlabeled samples from the identical distribution, these approaches mainly focus on propagating the correct information from the labeled samples to their neighbors. In contrast, the semi-supervised domain adaptation problem assumes that there is a significant distribution divergence between the source and target domains, and the given label samples are dominated by the source samples. Since Correctly predicted target samples are highly aligned with the source distribution, whereas incorrectly predicted target samples are located far from them. We can no longer assume that these target samples share the same distribution. Thus, the conventional semi-supervised learning approaches only propagate the label information within the aligned subdisk and the source distribution. On the other hand, the ultimate goal of domain adaptation is to enhance the discriminability on the target domain. And common unsupervised domain adaptation methods focus on reducing the inter-domain discrepancy. However, in semi-supervised domain adaptation, most of the error occurs on the unaligned target subdisk, and thus solving the problem depends on how far the unaligned subdisk is aligned. Since the existence of the unaligned target subdisk causes underestimation of the inter-domain discrepancy. Thus, the inter-domain discrepancy minimization approaches work less effectively. Moreover, since the aligned target subdisk is aligned in a class-aware manner, such approaches can even negatively affect. To address the intra-domain discrepancy, we introduced three schemes called attraction, perturbation, and exploration. These are the overall framework of our proposed method. Our framework consists of the feature extractor, trainable class prototypes, supervision module, and each module for the proposed schemes. The class prototypes and all normalized features of the samples are embedded in the same spherical feature space. Attraction scheme directly minimizes the estimated intra-domain discrepancy. To approximate the intra-domain discrepancy, we compute the feature distribution divergence between the aligned subdisk and the unaligned subdisk. However, since the labeled target samples are not sufficient to represent the aligned subdisk, but it is highly aligned to the source distribution, we instead use the complex distribution of source and labeled target samples. To practically achieve the divergence, we adopt maximum mean discrepancy. Defer to the conventional adversary perturbation scheme. Our perturbation scheme temporarily perturbs the aligned subdisk toward the intermediate region of two target subdisks to propagate the correct information to the unaligned target subdisk. The exploration scheme aims to locally modulate the prototypes in a class-aware manner, complementary to the attraction scheme, while selectively aligns the unlabeled target features via suitable criteria complementary to the perturbation scheme. To practically achieve this, we selectively collect unlabeled target data with its element-wise entropy less than a certain threshold, then apply a cross-entropy loss with the class of the nearest prototype. We evaluate the proposed schemes on three benchmarks: DomainNet, OfficeOM, and Office. The comparisons are MME, SegNet, DANN, ADR, CDAN, and ENT. As shown in the table, our method outperformed other baselines on average on the DomainNet dataset. And this superiority is still maintained in the OfficeOM and Office. Finally, we conducted ablation study on varying number of target labels. We adopt ResNet 34 and compared mean accuracy on DomainNet. Here, our method still shows superiority on other baselines across all numbers of target labels. Another notable thing is that ENT, one of the semi-supervised learning methods, also significantly enhanced the accuracy for a large number of target labels. And it even outperformed the state-of-the-art semi-supervised domain adaptation methods. This result is quite reasonable, since the increasing ratio of the labeled target samples assimilates the semi-supervised domain adaptation problem to the semi-supervised learning problem. To conclude, we introduced the intra-domain discrepancy issue within the target domain in the semi-supervised domain adaptation problem. Then, we proposed attraction, perturbation, and exploration schemes that addresses the intra-domain discrepancy.